Feeling like taking a coffee break? So do I. What about we talk about the Collection API, one of the oldest and most widely used API of the JDK. The first version of the Collection API was published in the JDK 1.2 back in 1998. And it's still pretty much alive, since the last update is a final feature of the JDK 21. This addition to the Collection API is called SequencedCollections. This is the JEP 431, and its goal is to model collections with a defined encounter order. Now, what does that mean? Let us talk about all that and visit this API again. Maybe you already know many things about the Collection API, but maybe you will still discover one or two things here and there in this JEP Cafe. The first version of the Collection API was super simple. Two hierarchy of interfaces, one for collections and another one for maps. The first hierarchy starts with a collection interface, extended by set, and list on another branch. No duplicate in a set, which is extended by SortedSet, that keeps its elements sorted. On the other hand, list tells you that when you add elements in a certain order, let us say A, B, and C, then when you iterate over these elements, you will first meet A, then B, then C. You can't do that with sorted sets. You can add A, B, and C, but when you iterate over these elements, the encounter order is imposed by the comparison logic. From this point, you already need to understand two notions. First, what does sorted mean? And second, what does ordered mean? And third, what's the difference between the two? So let us take a look at all that. Let us start with the sorting of elements. Sorting elements means that you need to use a comparator. This comparator can be embedded in your objects, and in that case they implement comparable, or it can be an external comparator, and in that case it will supersede the possible comparable nature of your objects. What can you do with the sorted collection? Let us examine three operations: getting an element from a given position, removing an element from a given position, and adding an element at a given position. If you have a sorted set, you can certainly get the third element from that set, and because you can access it, you can also remove it from the set. But there is no way you can tell, hey, I would like to insert this element in the third position. You can add an element, and this element will be inserted according to your comparison logic. It may land anywhere in your set. Ordering elements, on the other hand, means that each element has an index, and this is what lists are doing. In a list, you have an internal, maybe implicit or virtual, series of integers starting from 0 all the way to the size of this list. This could be represented by an array, for instance, even if it can be something else. If you add an element to a list, it will take the next index. Because elements have indexes, the three operations we just saw all make sense. You can get the third element and you can remove it. And you can add an element at a given position, something you cannot do with a sorted set. If you insert an element in a list, then the index of all the elements after this one is incremented. And if you remove an element from this list, then the index of all the elements after the one you removed is decremented. There are some fundamental differences between the elements of a list and the elements of a sorted set. First, adding an element to a list does not modify the index of the existing elements, because you add it at the end of the list. Adding an element to a sorted set may change the order of this set, because you cannot control where your element will land in this sorted set. So let us talk now about this encounter order. The encounter order is in fact the order in which an iterator will iterate through the elements of the collection, whether it is a set, a sorted set, or a list. And now there is the theory and what is happening really. Because it turns out that the most widely used implementation of collection or list in Java is the same, and of course it's array list. So even if the encounter order of a collection is not guaranteed, it is always the same, because what you're really using is an array list. For list, no problem. The encounter order is always the same, that's the semantic of the list interface, whether you're using array list, which is of course your best choice, or linked list, which you should not be using anymore. For sets, things are a little tricky. Odds are that you're using HashSet as an implementation for your sets. Adding elements to a set does not guarantee the same encounter order. And in fact, adding more elements may change the existing encounter order of the previous elements. For instance, suppose that you have this hash set with the following elements that you've been added to it. Well, if you add just one element, 13, then this order becomes different. Internally, there is a hash map in a hash set, and in the hash map there is an array. If this array becomes full, it will be copied to a bigger array. And during this process, all the key value pairs stored in this array will be rehashed in a new array. And this may change your encounter order. So your code should absolutely not rely on any kind of stability of this encounter order in the case of sets. But if you really need it, you can also use another implementation of set, which is called LinkedHashSet. Internally, LinkedHashSet is built on the linked hash map that has a linked list to iterate over its elements. This internal linked list gives you the stability of the encounter order. So whatever elements you add to a linked hash set, you will always visit them in the same order. This linked hash set class is an implementation of set, which makes sense because it does not allow doubles, and it has a property of lists, which is you always iterate over its element in the same order. Does it have all the properties of lists? Not quite. Could you get the third element of a linked hash set, for instance? That is, an element from an index. The answer is yes. Could you remove an element from a given index? And the answer is still yes, you can also do that. Could you insert an element at a given index? Well, not really, because adding an element to a set may fail if this element is already present. So the fact is, linked hash set has some properties that lists have, but not all of them, which prevents it from implementing Java util-list. So just to wrap things up, on the one hand we have ordered collections called lists, and on the other hand we have sorted collections called sorted sets or navigable sets. And in the middle we have linked hash set. All these are different, but they share some common behavior. And the fact is, as of now, there is nothing in the collection API to model this shared behavior. And this is precisely the gap that JEP 431, called Sequence Collections, aims to fill. Sequence collections are modeling a common behavior shared by ordered collections and sorted collections. What behavior has been selected? Well, 3 operations: getting, adding, and removing. And from 2 places in the sequence collection, the start of the collection and the end of the collection. That makes 6 methods: get first and get last, remove first and remove last, add first and add last. And there is a bonus method, reversed. How do these methods map to existing methods? Well, sometimes well, and sometimes not so well. If you consider the list interface, for instance, you can call getZero, removeZero, or addZero with an object. So operating on the first element is okay, it works well. For the methods that operate on the last element, it's not doing that great. Add operates on the last element, so this one is okay. But to get the last element, you need to call get and pass size -1. And the same for remove. You need also to pass size -1, which is not so great. So these two operations are not really supported directly. And for the last one, reversed, well, you can call collections.reversed and pass your list as an argument, which is not that great neither. For SortedSet and NavigableSet, the situation is better for getting the first element, which is actually the smallest, and the last element, which is the greatest. You actually have two methods for that, first and last. But when it comes to removing the first element without getting it first, then all you can do is use an iterator and call remove on it, which is really not great. And for the removal of the last element, it's even worse. You don't want to see the code. These new methods brought to you by SequencedCollection make these 4 operations much simpler. So that's basically the first step of introducing sequence collections in the collection API. Sequence collection extends the collection interface, and the two interfaces list and SortedSet extend the sequence collection interface. There is still a little detail to sort out. Sequence collection has a reversed method that returns the sequence collection. In the case of a sorted set, this return type should also be a sorted set. To implement that, another interface has been added called SequencedSet. SequencedSet extends sequence collections and override this reversed method that now returns a sequenced set in that case. That's the first part of the modification of the collection API. We talked about LinkedHashSet earlier and its specific behavior that was not previously captured by any interface in the collection API. Well, this is not the case anymore because now LinkedHashSet implements SequencedSet, which is great. Before we jump into the map interface and we see how the SortedMap and NavigableMap can benefit from sequence collections, let us take a look at the queue hierarchy. A queue interface was added to the JDK 5 back in 2004 as an extension of the collection interface. And in the JDK 6, the Deque interface was added as an extension of queue. The 3 basic operations on the queue structure in any language are super simple. You can push an element to a queue, you can pop an element from that queue, and you can check for the next available element with pick. These 3 operations, push, pop, pick, are the same in any language. Now things have been made a little more complex than that in Java, because there are different ways to handle the fact that the queue may be full if you want to push an element to it, or empty if you want to pop or pick an element from it. The choice was made to model 2 behaviors. For push, return false or throw an exception. And for pop and pick, return null or throw an exception. So in the end, the queue interface defines in fact 6 methods, 2 for each operations. Then the Deque interface was added in the JDK 6, and the idea of the Deque interface is to support both FIFO queues and LIFO stacks, with different behaviors when the Deque is empty or full. And Deque ends up with more than 20 methods, which makes it a little hard to understand at first. Because you can add, remove and get elements from the head or from the tail of a deck, it then makes sense to make it extend sequence collections, and this is what has been done. So now a deck is also a sequence collection, which may be useful to make your code simpler. Now that we covered the collection hierarchy of the collection API, let us take a look at the map hierarchy. It turned out that this hierarchy is almost the same, and in fact a little simpler because there is no equivalent to the list interface. So at the top you have the map interface, extended by SortedMap and NavigableMap. By the way, NavigableMap is an edition of the JDK 6, and there is really no reason to use SortedMap instead of NavigableMap nowadays. You can iterate on several elements of a map. First, the entries of the map, that is the key value pairs, modeled by the map.entry interface. You can get the set of the entries with the entrySet method. It is a set because you cannot have doubles among these entries. Second, you can iterate over the keys of the map that you can get with the keySet method. That also gives you a set. For the same reason, you cannot have doubles among the keys neither. And third, you can iterate over the values of the map that you can get with the values method. Now, you can have doubles among the values, so what you get is a plain collection, not a set. Note that what you get are actually views on the content of the map, and you can use these views to remove elements from a map. You cannot add anything, that wouldn't make sense, but you can remove stuff. Iterating over the elements of a map follows the same rules as for regular sets or collections. They are not ordered and not sorted. But if what you have is a sorted map, then iterating over the set of the keys or the set of the entries follows the ascending order of the keys or entries. And in a case of NavigableMap, you have two more methods, Navigable KeySet and Descending KeySet, that both give you a navigable set, which are views on the keys of this map, in the ascending order or the descending order. You do not have any equivalent for entries, unfortunately. So what's in it for you in SequencedMap? Well, first, the set of the keys and the set of the entries are now SequencedSet, and the methods are called SequencedKeySet and SequencedEntrySet. And by the way, there are still views on the content of your map. And second, you have a reversed method that gives you a reversed view of your map. Third, you have a putLast and putFirst method, which are supported by LinkedHashMap and not SortedMap, for the same reasons as SortedSet. And as a bonus, you get a fourth set of methods already present on NavigableMap, first entry and last entry to read the first and last entry, and poll first entry and poll last entry to remove the first and last entry of your map. The collections factory class got some love too in this JEP. You know that you have a family of factory methods to create unmodifiable views on collections, like unmodifiable collection, unmodifiable list, or unmodifiable set. Well, three factory methods have been added to this family: unmodifiable sequenced collection, unmodifiable sequenced set, and unmodifiable sequenced map. All these three methods create unmodifiable wrappers on the sequenced elements you pass as an argument. And with this, I'm out of coffee, so that's it for today. Talk to you soon.